All right, welcome back to Physics 221. So let me just remind you, we're talking about relative motion, so we have two reference frames. So S prime, the reference frame S prime, is moving to the right with velocity v relative to reference frame S. And again, we don't know anything about S. It could be moving, it could be at rest. We don't care. The important thing is that S prime moves relative to S. And the last thing we did, we were talking about the fact that time is relative. So we figured out that the time interval that we measure in S equals gamma delta tau, which is what we measure in S. Well, delta tau is what we measure in S prime. And remember, delta tau is just delta t prime. I wish I would have just kept it delta t prime, but whatever. So we're going to do some examples now. But before we do the examples, we need to learn about something called a light year. Now, when you think of that term light year, you think, oh, it must be time, right? Light year, time, but it's not. So light year is actually, it's a distance. So a light year is the distance light travels in 1 year. Now, here's what it is in meters. I don't really want you don't have to know this. This is the important thing. The light year is the distance light travels in 1 year. The only reason I showed you that, just to show you that it's really, really far. So here's an example. So the distance from Earth to Proxima Centauri, which is the next nearest star, other than the sun, right? I mean, that's how many kilometers? Well, ridiculous, right? And so astronomers, they don't deal with kilometers, they deal with light years. So we know that this star is about 4.24 light years away from Earth. So that's what you need to know. By the way, this is kind of an interesting question. So that means it takes light, 4.24 years to travel from the star to the Earth. And so, as we were talking about the other day, when you see this star, what are you actually seeing? You're actually seeing what the star looked like 4.24 years ago. All right, so let's see how this is going to be helpful. Okay, so let's just go back to basics. Velocity is distance over time, and therefore, what we have is the speed of light, right? Because we're talking about light. So I'm going to say the speed of the light is distance over time. So let's let the distance be 1 light year. Well, how long does it take light to travel 1 light year? Well, 1 year, right? 1 year. So 1 year. Now, we don't have to stop there. We can also say something called a light hour. Well, how long does it take light to travel 1 light hour? An hour, right? 1 hour. And we can say, 1 light minute over 1 minute, whatever. 1 light second over a second, on and on and on. So we can do whatever we want to do, whatever's convenient. Okay, whatever's convenient. Yeah, all right, okay. So this is a nice way to write the speed of light. The speed of light, again, 1 light year over 1 year, so forth and so on. And this is going to help us once in a while on certain problems. So we kind of want to remember that. So the speed of light is distance over time. Yeah. All right. Let's do an example now. So we're going to do some examples, these relativity problems, and there's a certain method. And what I want you to learn is the method, how to approach these problems. Okay, so here we go. In 1998, using the Keck telescope, scientists discovered some previously undetected young stars that are 150 light years from Earth. Suppose a space probe is flown to one of these stars at a speed of 0.98 c. The battery that powers the communication system can run for 40 hours. will the battery still be good when the space probe reaches the star? Okay, now, what would Isaac Newton say? Well, come on, it's 150 light years away, so that means it's going to take light 150 years to travel from the star to Earth. 150 years, right? But the battery can only live for 40 years. So Isaac Newton would say, absolutely not. The battery's not going to be, the battery will not be good when the probe reaches the star. That's what Isaac Newton would say. Well, Isaac Newton didn't understand relativity, so let's do it the correct way. So again, this is what I would say is the best way to approach these kinds of problems. All right, so number one question, what are the two reference frames? So number one, the two reference frames. So obviously there's Earth, and then there's a space probe. Okay, now, what are the two events? Well, hopefully you understand that the two events, the first event is when the probe leaves Earth. The second event is when the probe reaches the star. Stars, okay? So the events, so leave Earth and arrive near star. Okay, all right? Now, who or what measures the proper time, delta tau? Now remember, the proper time means that that reference frame's at the same location at both events. Okay, so, you know, think about it. Here's the Earth. Here's the stars. There's a probe, right, that goes from the Earth to the stars. Here's event 1. Here's event 2. So is the Earth at the same location? I mean, is the Earth here and is it the Earth here? Certainly not, right? How about, but the probe, is the probe here? Yes. Is the probe here? Yes. So the probe measures proper time. So 3. So probe measures proper time. And of course 4, who or what measures dilated time? We do, right? Earth, or what do you want to call it, right? So Earth measures delta t, the dilated time. So I'm being kind of lazy, right? I should say a person on Earth measures delta t, but that's a waste of time. Okay, so now what we want to do is we want to just start calculating. Okay, so delta t, again, so delta t equals gamma delta tau, right? All right, and delta t is measured by the Earth. So what would we say is the time? So what would we say is the time? Okay, so all we would say, you know, delta t, again, this is delta t from the Earth. It's just, you know, the distance over the speed. All right, and the distance is 150 light years. Okay, now we want to be clever, right? So the speed of light is 1 light year over a year, but we have 0.98 c. So the speed is I'll just do it 2 steps, 0.98 c, but that's no good. We want things to cancel. So we're going to say 150 light years, and then we're going to say 0.98 light years per year. Light years per year. And see, that's cool, right? Because then things cancel. And so you work that out, you get 153 years. Okay? So according to us, on the Earth, it's going to take the probe at this speed 153 years to go from the Earth to the stars. That makes sense, right? That makes sense. Okay, so delta t is 153 years. But who cares? I mean, the question is, you know, will the battery still be good? The battery is in the probe, so we don't care about, the time according to the Earth. We care about the time according to the probe. So what we really want to calculate is the proper time. So let's do it. Okay, as always, whenever you have a relativity problem, the first thing you have to do is calculate gamma. So like I said the other day, so gamma is 1 minus beta squared negative 1/2 power. So you get 1 minus 0.98 squared negative 1/2 power. Don't forget to square it, right? And that comes up to be a nice number, believe it or not, 5. Can't believe it. All right? Okay, so we want delta tau. So delta tau equals delta t over gamma. So it's 153 years divided by 5. That's 30 point something, 30.6 years. Okay? So according to the probe is only traveling, according to the probe, right? According to the probe is only traveling 30.6 years. Well, the battery can last for 40 years. So will the battery be good when the probe reaches the star? Yes! All right, so the answer to the question is yes. The probe will still be good. The battery will still be good when the probe reaches the star. Now, that's a pretty awesome example, right? I mean, it just shows you that Newtonian physics just isn't able to handle something like this. Okay, so I hope you're impressed by that problem. Let's do another one. An airplane flies from San Francisco to New York, about 4,800 kilometers, at a speed of 300 meters per second. How much time does it take the trip as measured by an observer on the ground and an observer in the plane? Now, you should know by now, 300 meters per second is nothing compared to the speed of light. So we're not going to have a huge difference in time. I mean, here, come on, this was huge, right? 153 years versus 30.6 years. It was huge because the speed was 0.98 c. I mean, gamma was 5. But here, this is pathetically slow compared to the speed of light. So it's not going to be a large effect. But I'm going to teach you something that's useful when you have these types of problems. Another tool for your toolbox. So that's why we're doing this problem. Same approach, right? Same approach, but you'll see. Okay, once again, so, here's Earth, right? So here's San Francisco, here's New York, right? Okay, so what are the two reference frames? Well, the ground, or the Earth, whatever you want to call it, and the airplane, right? So there's the ground and there's the airplane. What are the two events? When the airplane leaves San Francisco, when the airplane arrives in New York City. So takeoff and landing, however you want to call it. All right, now you have to get these questions right in order to solve the problem, right? This is the crucial one. Who measures proper time? It's the airplane. Agree? It's the airplane, because the airplane is right here at the beginning, right at event 1, and the airplane is right there at event 2. All right? So the proper time is the airplane. Proper time is measured by airplane. Okay? And who measures the dilated time? The person on the Earth. So dilated time, someone on Earth. Just like the last problem, very similar. Okay, so calculate delta t. That's just like what you and I would normally do, Calculate delta t. So delta t, that's distance over speed. So the distance is 4.8 times 10 to the 6th meters. And the speed is pathetically slow. And you get 1.6 times 10 to the 4th seconds. All right. Now, as always, we have to calculate gamma. Okay, so gamma, 1 minus beta squared, negative 1/2 power. So, oh gosh, so it's going to be 1 minus 300 meters per second all over 3 times 10 to the 8th meters per second squared, negative 1/2 power. All right, now, so I want all of the students, please, to pause your video now and use your calculator and figure this out. So pause your, this is crucial, all right? So students, pause your video, figure this out using your calculator. All right, so I assume you've done that. So with a normal, good, everyday, wonderful scientific calculator, it can't handle this, right? It doesn't have enough digits or whatever. So you're just going to get 1. Well, it's not 1. Come on. How could it be 1? You get this thing there, right? Okay. So that's a problem, right? It's not a mathematical problem. It's a problem with your calculator. It just doesn't go far enough, you know. So what are we going to do? Okay, so here's a little math thing that you're going to learn. Again, this is the toolbox, right? Another tool for your mathematical toolbox. Okay, so a long time ago, somewhere along the line, you hopefully learned the binomial theorem. So a minus x to the n power, a to the n, on and on and on and on and on. Okay. Now, what we have is a 1 minus something, right? So let's put a 1 for the a. So everywhere you see a, you put a 1. So we have 1 minus x to the n power. Okay. Now, what? Okay, sorry. So that box or that rectangle is supposed to be this. X is much less than 1. All right, that's what it's supposed to say. For x much less than 1. Because that's what we have, right? This here is much less than 1. So what we want to do is look at this equation for really, really small x compared to 1. Now, so if x is super small compared to 1, what's x squared going to be? Super small, so just ignore it. How about this? X cubed. Super small, and all this, okay? So basically, if x is super small compared to 1, you can just ignore all these, and it will be just fine. So what do you come up with? So you just have 1 minus nx. 1 minus nx. Okay, cool. Now, what we have, though, we have 1 minus something small to the negative 1/2 power, right? So our n is negative 1/2. So that means it's going to be 1 plus x divided by 2. Okay? So, all right. So all right. So this is something that we use a lot in relativity. So let's write that down somewhere. So 1 minus x to the minus 1/2 power is equal to 1 plus x over 2. Okay? So that will help us because our calculator doesn't help us. All right. So again, what we want is this, right? We want this. So according to this approximation, this is approximately equal to 1 plus this thing, 300 meters per second over 3 times 10 to the 8th meters per second squared divided by 2. And I promise you, if you do that, you get something like 1 plus 0.5 times 10 to the minus 12. Okay, so that's what your gamma is. So gamma is 1 plus 0.5 times 10 minus 12. Well, what's that? I mean, it's pretty close to 1. Agree? It's pretty close to 1. But, hold on. So we want delta tau. So delta tau is delta t divided by gamma. So that is 1.6 times 10 to the 4th seconds divided by 1 plus 0.5 times 10 minus 12. And, you know, all I'm going to say, it's less than 1.6 times 10 to the 4th seconds, right? But not by much, just barely less, but it is less, okay? All right. So I guess what I should say is that it's really very silly to do a problem like this with relativity because the speed is just too small, right? But again, the only reason I showed you this problem is so I could show you this approximation, which we use a lot. All right, so I spent a long time going through time dilation. I motivated it with the light clock and so forth and so on. Well, now I'm going to talk about something called length contraction, and I'm really not going to motivate it. I'm just going to give you the result. So here we go. So what am I saying? I'm saying if I have a meter stick and I'm running relative to you, I measure the length of my meter stick to be a meter. You will measure something less than a meter. So length is relative. Length is relative. Physicists use the term space is relative, but what they mean is length is relative. So here's the equation. So uppercase, and this is just what Randy Knight uses. Other people use different notation. Uppercase L prime equals lowercase l divided by gamma. So the contracted length equals the proper length divided by gamma. So if I'm running relative to you, the proper length is 1 meter. Okay? So here's the graph. So this is, all right, so I have a meter stick, right? And if I'm standing stationary and you measure the length, you're going to get a meter. However, if I run at 0.5 c, you would actually measure the length of the meter stick to be like 0.86 meters or something like that. Okay? So the length depends on the speed of the reference frame. So here's kind of there, all right? So the length of objects appear to be contracted, shortened when they move by us. So you can see here, right? So this person is holding a meter stick, and this guy was holding it, or whatever, this alien was holding a meter stick, but it looks to be shorter. And this only happens in the direction of motion, right? Only in the direction of motion. That's important, right? So in other words, you know, if I'm doing this is not going to shrink, right? It's just that the width of the meter stick will shrink because it's only in that direction. Okay, so once again, here's this proper business again. So the proper length, lowercase l, in a particular reference frame is a length measured on an object at rest in that reference frame, right? In my reference frame, the meter stick is at rest. So I would measure the proper length to be 1 meter. The shorter length, uppercase L prime, is the length between the same 2 points on the object, you know, one end to the other end, as measured in a second reference frame that has speed v relative to the first. So if I'm doing this, according to me, you're moving, I'm stationary, right? So you're going to measure the shorter time. Okay, here we go. So you watch a spaceship fly by at 0.75 c. Compared to an astronaut in a spaceship, okay, so students, pause your video and figure this out. All right, we're back, so let's do it. So you watch a spaceship fly by at nearly the speed of light. So you are measuring uppercase L prime. Remember, gamma is always greater than 1. So it will be shorter, right? Just look like this, right? The length of objects appear to be contracted, shortened when they move by us. So you would say that the spaceship is shorter in the direction of motion. Okay, we're going to do some examples, but we're going to stop right now. Okay.